quickly introduce the speaker. So the second speaker is yuze. He's currently a PhD student at the Computer Network Information Center at the Chinese Academy of Sciences. His research focuses on low Earth orbit satellite network topology optimization, space-ground integrated routing, and link planning under physical hardware constraints. With that, I'll pass the time to yuze.
Thank you. Good afternoon, everyone. I'm Yuze Liu from the Computer Network Information Center, Chinese Academy of Science. And in presentation of my PhD supervisor, Yanbiao and gaogang, I want to tell you about our work, BiCayley, a traffic-aware way to design 3 inter-satellite link topologies using Bipartite Cayley graphs. The question we try to solve is very simple, is that how do you pick the right 3 links for every satellite when the global traffic is far from uniform? And let me start with why we try to research the 3 links problem. Nowadays, the low Earth orbit satellites are becoming the backbone of the integrated space terrestrial network with laser intersatellite links carrying up to 200 gigabytes per second. For years, the academic default has been a 4-link grid, whatever the X grade, star grade, or motive. But the industry has already removed the 4th link due to the size, weight, and power consumption constraints. The main operators like Starlink, they only carry 3 laser terminals in one satellite. And according to their report in 2025, there are roughly 24,000 optical intersatellite links in orbit and around 8,000 satellites in orbit. It means every satellite has only 3 links, and it challenges the 4-ISL grid topology. And that's why we have to design a 3-ISL topology. And why the existing 3-ISL design for short? First, most of them are traffic agnostic. Take the honeycomb topology as an example. It proves one of the 4 links and form a honeycomb topo. And in this pattern, it will force traffic into zigzag passes and inflate the latency, especially in asymmetric shares. You can see it from the picture. And second, the repointing links to chase instantaneous demand creates link chains. The signaling and establishment of inter-satellite links can take minutes, which is unacceptable for delay-sensitive traffic. And third, distributed link selection leads to coordination bottlenecks. Satellites will compete for the same port and end up with inconsistent topology. What we need is that the traffic-aware, zero handover, and conflict-free topology. And let me formalize the problem first. In order to optimize the topology, we define a traffic-weighted cost. We use the demand between different city pair, the city U and the city V. We multiple demand with propagation delay and per hop processing delay, which here is air and edge. And our objectiveness is to minimize the aggregated cost of the topology. And this problem is under 3 constraints. First, every satellite should have exactly 3 links, and second, the links must be astrodynamic feasible. It should be within 4,000 kilometers and within the tracking and the relative velocity and angular velocity. And last, the graph must stay connected. And this problem is an anti-hard problem because it's a degree constraint variant of the optimal communication spanning tree. For a share with over 15,000 satellites, the search space is super exponential. Exact solvers simply cannot reach it. And next part, we will give you our key insight. Because the warp delta constellations are highly symmetric, they form a discrete torus, and in degree 3 undirected graphs, bipartite construction gives us vertex transitivity. So every satellite sees an identical local structure. That means we don't have to search over a gigantic adjacent matrix at all. What all we need to do is just find 3 generator offsets, and every satellite can use these offsets to form a whole graph. And here comes our construction process. First, we need to partition the satellites into 2 groups by their index in orbit. And in the forward mapping function, every even class satellite connects along these 3 generator offsets, and in the reverse mapping, all class satellites connect back along the same offsets. And as you can see, the figure 1 on the right shows the result. For the share 5 of Starlink, we pick 0, 1, 1, 0, and 1, 2 offsets, and we form this topology. And on the right is share 2 of Starlink, and we pick another offset to form this topology. Of course, not every triple offset is valid. We have to filter them. We filter them in 2 stages. First is structural parity. The generator must map between 2 partitions, which keeps the graph bipartite and free of self-loops. Second, it should be astrodynamic feasible. The link must survive the whole period, the whole orbital period. The distance limit at the equator is where the interstellar links has a max distance, and the velocity and angular velocity limit at high latitude where they have more motion dynamics. And after pruning, only dozens of candidates remain for per share. So searching triples of them is polynomial, roughly 10,000 to a million candidates instead of something super exponential. And the next part, we use parallel simulated annealing method, because even after filtering, we are still left with tens of thousands candidates triples to rank, and finding the best one is very time consuming because we have to calculate the shortest average path for all the city pairs in the graph. So we propose the parallel simulated annealing method. This search is driven by 4 primitives. First, exploration. Neighborhood generation perturbs the current triple inside the valid set. And the second, pruning, is a faster breadth-first connectivity check to skip the fragmented topologies. And third, evaluation. We use Jonathan's all pairs shortest path, exploits the 3 regularity of BiCayley, keeping the per candidate cost near quadratic. And finally, the acceptance. We use a metropolis rule to balance the exploration and the exploitation as the temperature cools. And because every candidate can be scored independently, we distribute the evaluation across many walkers, so the search converges to a nearly optimal traffic-aware triple in about 10 minutes, even for ultra-dense constellations like Share 2 with over 1,500 satellites. And here comes our experiment part. We use 4 Starlink shares with very different geometries. We define the share 2 and 3 as asymmetric. As you can see, its plane number is much bigger than the satellite number per plane. And share 5 and 6 are nearly symmetric because these 2 numbers are nearly equal. And we use traffic comes from the top 500 GDP ranked cities using a gravity model. And we compare our method against the 4-link grid and the 3-link honeycomb baselines. And here comes the result. In the asymmetric share, like share 2, the BiCayley extraordinary bypass the 2 baselines. It cuts average shortest path length, what we call ASPL, by 80% and average hop count by 63% compared to honeycomb. And it even beats the 4-link grid topology by 46 and 43%. And honeycomb's ASPL exceeds 29,000 kilometers, while BiCayley stays under 6,000. And while in symmetric shares, BiCayley matches the grid. On share 5, it improves on the grid's average shortest ASPL, and on share 6, it stays within 4.5% of a 4-link grid baseline, while using 25% fewer laser terminals. That is essential great class performance at 75% of the hardware. And the stability across 120 snapshots, covering a full orbital period. Share 2 keeps a mean ASPL of 80.6 meters with a standard deviation under 1.2% and a maximum jitter of 341.5 kilometers. Share 6 is even tighter. It's because every node sits an identical neighborhood. The global path metrics are rotation invariant, so the quality of service stays predictable. And last, our conclusion and outlook. The BiCayley delivers a traffic-aware zero handover, conflict-free three-link topology by exploiting consideration symmetry. We use 3 generator offsets instead of search over the whole adjacent matrix. And our method can matches the great baseline performance while using 25 fewer links, and that's saving a lot of energy and cost. Looking ahead, we plan to add self-healing under link failures, incremental updates for bursty traffic, and scaling loss for heterogeneous multi-share considerations. And that's all for today's sharing. And thank you, everyone. And I am glad to answer your questions and have a discussion. Thank you.
All right, okay. Do you have any questions for the speaker? Please.
Okay, thank you. Thank you for your presentation. In your evaluations, your work outperforms the traditional 4-ISL grid in asymmetric scales like solid shell 2. Why can 3-ISL topology achieve lower latency than 4-ISL grid that has more hardware links?
Oh, okay. Thank you. And I think it's a good question. In share 2, I think it's a very asymmetric share because the plane numbers is much bigger than the satellite number per plane, which means the distance between the shares is much smaller than the actual distance between the satellites within the same orbit. And while in the grid, it will force the satellites to go to the high latitude first, and then it will cross the links in the same share. But our BiCayley methods, it uses a 3 generator offset. It will create the shortcut between the satellites from different shares, and which will reduce the overall average shortest path length, and thus reducing the propagation delay. And that's why we can outperform the 4-ISL grid method in the very asymmetric configurations. Yes. Okay.
Maybe one last question.
Thank you for your presentation. I have one question. How resilient is this technology? Is the service or literally suddenly falls in orbits? Does a single false rate the weakness, transparency or overall networking duty?
Okay. Thank you for your question, and I listed this problem here. And in this work, we haven't considered the fault tolerance design, but in our future work, we will complete this. But in recent design, it has some ability to account for the unprecedented fault, like some links breaks. But in the topology itself, it has some redundant paths to route the traffic, and in the future we will consider pre-calculation to prepare for the link down event, and that's all. Okay, thank you.
All right, let's thank the speaker again.